Hello. So, as we discussed the need for developing approximate solutions to the governing differential equation, the method of weighted residuals is the most commonly used technique, and it constitutes the basic idea behind method of weighted residuals is that based on the basic idea of linear algebra, that any function can be any finite function can over a finite domain can be represented by a linear combination of linearly independent basis functions, as long as that family of basis functions constitutes a complete basis. So, it spans the complete function space or vector space. So, as long as we are assured of generating or spanning the complete space, it should be possible to construct an approximation for any finite function over a finite region by suitable linear combination of those basis function, and if the basis functions are polynomials, then that particular case is covered by Weierstrass approximation theorem that we had discussed during interpolation theory. So, the basic idea is we seek an approximate solution. So, if u of x is the true solution, so we do not look to find u of x exactly. Instead, we try to approximate, we try to find an approximate function u hat of x as an approximation to the unknown function u of x in terms of a series, as in a series form, such that using with a linear combination of basis functions, or they are also referred to as trial functions with unknown coefficients. So, the chosen functions, set of functions, as I said, using by taking reference to Weierstrass approximation theorem, the chosen set of functions should be linearly independent and they should represent a complete family of basis functions. That is, they should all the basis functions taken together, they should span the complete space, function space or vector space. So, in case of this is a function, so we are approximating function, so function space. So, a polynomial, for example, is an infinite family. We can keep on increasing the degree of polynomial and they are linearly independent. A constant term, there is no way a constant term can represent what is represented by a linear trend. There is no way a constant and linear term can represent what is contained in a quadratic function, and so on. So, a linear combination of increasing degree of polynomials constitute a complete family, and we can possibly construct any approximation which will in principle should be able to approximate or should be able to capture the sufficient details of any finite function over any finite region. So, we consider the approximation. So, u of x is approximated as u hat, and u hat is given by some function u naught x plus the linear combination c j g j. So, g j are the basis functions, set of linearly independent basis functions, and they satisfy what we call homogeneous essential boundary conditions. More on this essential boundary condition business little later. Kindly bear with me until that point. This distinction between essential boundary condition, what constitutes essential boundary condition, will become clear maybe after 1 or 2 lectures. But in this particular bar problem, let me just say that the essential boundary condition constitutes the boundary condition imposed on the displacement. So, if you recall the bar problem that we had discussed, there were 2 boundary conditions, at x is equal to 0, the boundary condition was imposed on the displacement. Axial deformation at x is equal to 0 was imposed as 0, and the other condition at x equal to L, it was the force boundary condition. The axial thrust was equal to the applied force. So, that is called the force boundary condition or natural boundary condition. So, in this particular case, for the construction of approximation, it is important that the basis function that we choose, they should be of a form which satisfy the homogeneous essential boundary conditions all over the problem, right. And u naught x is a function, some function which satisfies, if for example, in that bar problem, if I had specified deformation to be non-zero at x is equal to 0, then that is a non-homogeneous boundary condition. So, boundary condition, the deformation at x is equal to 0 is, let us say, equal to some constant. So, then that is a non-homogeneous boundary condition, and then that has to be specified. So, if it is a constant, then u naught x is simply that constant that is equal to the non-homogeneous boundary condition of the problem. And the series solution that you see Cj, Gj, they just operate on top of this non-homogeneous boundary condition function, and together complete summation that gives us an approximation to the problem. And Cj, they are the unknown coefficients, that these are not yet known. So, we have to find a way of how to determine these coefficients, and that is why the name weighted residual comes. So, that mystery behind the name will be clear just in a while. So, naturally, if we had true solution u of x, then it will satisfy both the governing differential equation and the boundary conditions exactly, and there will not be any error. The very fact that we are admitting the possibility that we are not looking for exact solution, we will be satisfied with an approximate solution as long as it is approximation is good enough. So, the moment I say approximate solution, the inherent implication is there are errors in satisfying the governing differential equation and the boundary conditions possibly. So, it will, the governing differential equation, that is Lu plus P, need not be equal to 0 all over the domain, right. So, the governing differential equation, this is what the governing differential equation is, Lu plus P is equal to 0 in omega. So, if I substitute approximate solution u hat in place of u, then it will not hold all over the domain, right. There will be an error because it is an approximate solution. So, this governing differential equation may not be satisfied exactly. Similarly, for the boundary condition, the boundary conditions may not be satisfied exactly on all the boundaries, right. So, there may be error in the boundary conditions as well, satisfying boundary conditions. So, those errors are referred to as residuals. So, if I substitute the approximate solution in the governing differential equation and the boundary conditions, then there will be an error of approximation, and these errors are referred to as residuals. So, we will have obviously two types of residuals. One is domain residual coming from the governing differential equation, that is r omega is equal to Lu hat plus P in omega, and the second error, second residual is the boundary residual r gamma, that is arrived at, that comes from the boundary condition. So, substitution of approximate function, approximate solution into the boundary condition. So, mu hat plus r on evaluated on the boundaries. So, these are the errors. Now, the quality of approximation obviously depends on how do we minimize these errors. So, that provides us the conditions, required conditions, or how the coefficients Cj's are to be evaluated. Cj's keep in mind, those are unknown coefficients of approximation. So, u0 here is known because that comes from the boundary condition of the problem. Gj are the known functions, that are what the basis functions we have assumed. Cj are the unknown coefficients of this summation, we do not know what these coefficients are. Now, these coefficients are to be evaluated by somehow minimizing this error of approximation, because the ultimate idea is to construct an approximation which is as good as possible, and what is as good as possible? The error should be as small as possible. Now, it is easier said than done. There are different ways of interpreting what is meant by small error, right. So, in the method of weighted residuals, we emphasize that we do not look at these errors individually, rather we would look at the errors, minimize, or we try to minimize, or we look forward, we look to make the errors vanish in a weighted average sense, over the entire domain. So, the domain error, domain residual multiplied by some weighting function, let us say W, and integrated over the entire domain of the problem, plus the weighted residual of the boundary. So, W bar is another weighting function which operates on the boundary residual, and this is evaluated, accumulated over the boundary, and these together they should vanish, and W bar are arbitrary weighting functions. Now, let us delve upon this. It is a very straightforward equation, but statement, but it has significant implications and very important results derived from this. First of all, the exact solution is contained in this statement. This weighted residual, this is called statement of weighted residuals. This particular W r omega integral plus integral of W bar r gamma equal to 0. This particular statement, expression is referred to as statement of weighted residuals. Now, the exact solution, if I knew what is the exact solution of the governing differential equation u of x, then obviously the domain residual and the boundary residual would vanish. R omega would be 0, R gamma would be 0, and this weighted residual statement would hold irrespective of what weighting function I choose. So, for any arbitrary weighting function W bar, whatever may be the W and W bar, if I know the exact solution, then R omega is identically equal to 0 all over the domain, R gamma is identically equal to 0 at all the boundary points all over the boundary, and this weighted sum of residual would be 0. So, the statement of weighted residual would be identically satisfied for any function, any arbitrary function W and W bar. So, that is a reassuring thought that what we are doing here, this particular weighted residual statement, the true solution, exact solution is contained in this. Now, think over this a little bit more. For any arbitrary choice of W and W bar, this weighted residual statement should hold if it was a true solution. Now, if I try to develop or try to find solution or try to satisfy this statement of weighted residual over a large number of W and W bar, then in a way I am approaching the true solution. If I consider arbitrary functions, I mean any arbitrary function, So, any arbitrary function would be let us say consider W1 one function, W2 another function, W3 another function, W4 another function, and so on. So, if I try to enforce this statement of weighted residual over different functions, arbitrary function I can choose. So, W1 r omega integral plus W bar 1 r gamma integral, that is equal to 0, that is one sentence, one statement, one pair of W1 and W bar 1. We take another pair W2 and W bar 2, again enforce it to 0, and so on. So, as we increase these number of weighted residual statements, we find that we will be approaching the condition imposed by true solution, that no matter what weighting function we choose, the weighted residual statement holds. So, if I consider a large number of these weighting functions and enforce this condition to vanish, then I am in a way approaching the true solution. Obviously, I cannot approach infinity on a for any thing on digital computers or for any finite operation. So, it remains an approximation, but an approximation that approaches the true solution, as the number of weighting functions over which for which this weighted residual statement holds will increase the degree of or quality of approximation, so to say. So, as I said, true solution of governing differential equation would satisfy the weighted residual statement for any arbitrary choice of weighting functions, since the residuals vanish at all over the domain and the boundaries. Now, for an approximate solution, we enforce the vanishing condition for a set of weighting functions W j and W bar j, and j can range from 1 to large number. So, the statement now becomes this integral. Now, we represent r omega by substituting the approximate solution u hat there. So, W j multiplied by r omega integrated over the domain, W bar j multiplied by r gamma integrated over the boundary, that is equal to 0, and this we do for different functions, different sets of functions j ranging from 1, 2, 3, 4 and any large number as required. So, how many terms that we need? Any large number. So, how far do we go? Obviously, we have some unknown coefficients to evaluate, and those unknown coefficients can be evaluated only when we have some conditions on those unknown coefficients, and that is what we will try to do. I mean, we will use these functions, as many functions as there are unknown coefficients. So, as many sets as there are unknown coefficients. So, if let us say if there are 3 term series, 3 term approximation involving 3 coefficients C1, C2, C3, we will have these 3 sets of equations for 3 sets of j is equal to 1, j is equal to 2 and j is equal to 3. We evaluate 3 statements of weighted residuals, and they give us some relationship, some equations in terms of C1, C2 and C3. We solve those 3 equations and we got C1, C2, C3 and substitute in our basic approximation, and we have the governing working approximation to the governing differential equation available. So, that in essence is the method of weighted residuals. Now, this has a very profound physical practical significance, and that cannot be overemphasized. What it does, what this method of weighted residuals does is to convert the problem of solving a differential equation. Solving a differential equation is a not a trivial task, I mean, to put it mildly. So, it transforms. So, this statement or this method of weighted residuals, as we have discussed, as we have developed it here, it transforms the problem of solving a differential equation into a relatively simpler problem, much simpler problem I would say, of solution of algebraic simultaneous equations, because after this evaluation of integrals, I mean once we have this some approximation of solution available in function u hat, the derivatives are all taken care of. So, differential operators are all taken care of, we only have some normal function or constant, and that has to be evaluated, that integral has to be evaluated, and at the end of this operation we will only have simple algebraic equations. So, simple algebraic equations in terms of unknown coefficients of the solution. So, C1, C2, Cj's that we have in this series solution, series approximation. So, we will have at the end of this weighted residual statements, we will end up with a series of simultaneous equations, algebraic simultaneous equations in terms of Cj's, C unknown coefficient C1, C2, C3 etc. And these unknown simultaneous equations can be solved using normal, I mean any usual equation solver, linear solver. You can use Cholesky method, LU decomposition, or Kraut, Doolittle, or even Gaussian elimination is fine. So, with partial pivoting of course, and the solution can be coefficients can be evaluated. Once we have these coefficients, those can be plugged back into this equation assumed form, function form, and that provides the basic approximation. Now, the quality of approximation can of course be improved by increasing the number of terms in the series. So, we can compute what is the error. I mean of course, we do not know what is the known solution. So, the error of approximation can only be gauged by considering how the refinement happens and what is the convergence of the by addition of the terms in this series. So, we will come to that convergence analysis, convergence of the solution. You might have discussed series convergence earlier in your mathematics course, but we will discuss it briefly to assess the convergence of this series approximation in solution of the governing differential equation. So, this is the basic idea of the approximate methods of solution. We are essentially trying to solve differential equation, governing differential equation, by transforming it into algebraic equations and then solve the algebraic equations for the unknown coefficients. And this is a very straightforward and very robust procedure, and that can handle many complex problems, many complicated situations for which analytical solutions may not exist, and we can still work out a very decent workable approximate solutions that can be used for our subsequent engineering analysis. So, we will continue on this with more examples. Let us take some examples. There are different versions of method of weighted residuals depending on how we choose these weighting functions. So, we will see how these weighting functions are chosen, or how the what are the different variations on method of weighted residuals, and then let us get our hands dirty. Let us work out some problems. I will discuss couple of cases, numerical, and then see how the solution varies, so that you get some idea, get some feel of the working of the method of weighted residual and gain some confidence that yes, this is an approximate solution technique, but it does work it does give us something meaningful, something workable to base our engineering judgment upon. So, thank you. We will continue with the variations on method of weighted residuals in our next lecture. Thank you.